Well, good evening, ladies and gentlemen. Let me welcome you to this occasion. Thank you so many of you for coming. I'd like to welcome also the people who have been attending the UK-India Solar Energy Workshop during the day, who decided to stay on for this event this evening. I'm Roland Clift, Fellow of this Academy, and I used to be a colleague of Hans Müller-Steinhagen, because you may or may not know that he actually spent 7 years at the University of Surrey as head of the Department of Chemical Engineering and then as head of school. Hans then returned to Germany, where he became director of the Institute of Technical Thermodynamics at the German Aerospace Center, and also director of the Institute for Thermodynamics and Thermal Engineering at the University of Stuttgart. Many of you, I'm sure, will know that Germany in particular has been very active in developing the concept of solar thermal energy, in part working with the research center at Almeria in the southeast of Spain. And Hans has actually been one of the key people in those developments. So we're particularly lucky to have Hans here this evening to explain to us what the plans are. The order of proceedings for the evening is that Hans will give us a talk. We'll then ask the two respondents to come up here. The four of us will sit at the table. I'll ask the two respondents to say some provocative things to get the discussion going. And then we'll ask for questions from the floor, which the main speaker and the two respondents will reply to and maybe discuss amongst ourselves. We're due to finish the discussion session at 7:45. If the discussion goes on a bit, I will let it run on a bit longer than that. But we have a reception following the formal proceedings, so if you want to take up any matters with Hans after the end of it less formally, then we've got a chance to do so at the reception. Professor Müller-Steinhagen.
Well, thank you very much, Roland. Good evening, ladies and gentlemen. It's indeed a great pleasure to be here and speak to you. I must say, I enjoy every time I come back to the UK, and it's still my home from home. Before I start talking about solar thermal power plants and electricity from the deserts, let me just introduce my own organization with a couple of slides, because not many people outside Germany would know the German Aerospace Center, DLR. And DLR is more or less the German equivalent to NASA in the United States. Of course, we are much smaller than NASA, but we still have a budget, an annual budget of 1.4 billion euro, out of which roughly 750 million are the German contribution to the European Space Agency and to the German National Space Program, where DLR is just the program manager. And then we have around 600,000 euro for research and operations, half of which is coming directly from the German taxpayer, and the other half is third-party income, which we attract worldwide. Now, this money is spent in 30 research institutes all over Germany, and my own institute has its headquarters here in Stuttgart, but we also have, for historical reasons, a department in Cologne, a department which we just started in Hamburg with Airbus, and we have for the past 30 years been present with roughly 15 people on the Plataforma Solar, the world's largest solar thermal testing platform in the south of Spain. Now, in total, the German Aerospace Center employs 6,200 people, out of which 2,800 are scientists with a master degree or a PhD. We have a significant number of doctoral students and postdocs and visiting scientists. And as the name says, 80% of our activities are in the area of space and aeronautics, 10% is in transport, and 10% roughly is in energy. And my department would have 80% of its annual budget of 25 million in the area of energy, but we also have some projects in the other areas. In total, my department employs 240 staff, out of which about 100 are working on solar thermal power plants and the related systems analysis and technology assessment. Now, what have we been doing to give this presentation. To make it very short, we have over the past 30 years developed most of the concept and the technology which is now going into this Desertec initiative, which I will be describing in what follows. It started 6 or 7 years ago when we did, on behalf of the German government, an analysis on the past, present and future electricity demand of 50 different countries in Europe, the Middle East, and in North Africa. And for these countries, we analyzed with a very high spatial and time resolution the required electricity and the potential to generate this electricity from a wide range of sources. Let's start with Middle East and North Africa. Don't even try to read the different countries. Believe me, we have done it for all of these countries. The important message is the following, that the electricity demand in the so-called MENA countries will increase by a factor of 5 to 6 over the next 50 years, reaching roughly the level of electricity consumption Europe has already now. This is because of increase in population, but also increase of industrial activities and increase in the quality of life. Now, if we look at this, this is the same plot here. That's the increase, and this is the capacity which can be produced by the existing power plants in 2000. These power plants will go out of operation over the next 30 years because of old age, and you see there's a tremendous gap that has to be fulfilled. That means there's a tremendous need to build new power plants in the Middle East and North Africa. This means investments, but also it means a potential to restructure the electricity market and to form closer economic, political, and social links with Europe. Now, how does the same situation look for Europe? Again, don't look at the individual countries. They are all there. The United Kingdom is here. That's this one here. As in Europe as well, the electricity demand will increase over the next 20 years or so, but it will then level off because of socio-democratic means and because of the high efficiency of electricity consumption and provision. If we move to a higher percentage of electric mobility, cars with batteries, this will not go down, but it will also tend to level off somewhere up here. It will make another 5 or 7%. Now, we could, of course, say, well, this is not too bad. We will manage with this amount of electricity or increase in electricity generation. But this is not the case, because if we look at our present electricity production capacity, this is the dark blue area, then we see that in Europe we will have to replace roughly 60% of our existing power plants over the next 20 years because they just have reached the end of their economic and technical lifetime. So again, there is a tremendous need to build new power plants. In addition to this, we have our targets to reach the reduction of CO2 emissions, to increase the percentage of renewables in our complete electricity mix, and of course, to reduce our dependency on imported fuels. So both areas, MENA and Europe, have to build a huge capacity of power plants, and the question is now, what power plants will this be, and how can we position this important area for the years to come? We looked at the whole portfolio of energy sources for production of electricity. So here the conventional technologies. We didn't look at fusion because fusion power will, if ever, only become economically relevant in later than 2050. We went up to 2050 in our scenarios and not further on. We looked then at the storable renewables, and we looked at the fluctuating renewables like wind, photovoltaic, wave, and tidal. Now, for each energy carrier and energy technology, we made a sustainability assessment and said they have to qualify in terms of affordability, security of supply, and compatibility. And if two technologies were equal in terms of availability and cost, then we always gave preference to the one which is more sustainable. Now, if we look at our energy scenario, I don't think there is any doubt that we have to increase the percentage of renewable energies in the future. I mean, even if there are discussions on the rate of doing this, on the other alternative technologies, I don't think there are many governments who would debate the need to increase the percentage of renewables. And so we did an analysis with a 10 square kilometer resolution, 30 minutes over the whole year, on the potential of different renewables such as biomass, geothermal energy, wind, hydropower, and solar for Europe and for the MENA region. And as you can see, just for an example, wind has more potential where the blue is dark, so around England, of course, and in the coastal areas is a significant potential for wind. You also get a fairly high energy density in terms of gigawatt hours electricity per year and square kilometers. Similar for biomass, there's, of course, in the Sahara Desert, there's no biomass. There's a lot more in Central Europe, and so on. And then we have solar energy, which has, surprisingly, the highest energy density of all renewables. We then calculated from all the different forms of energy the economic renewable potential to generate electricity. And the economic renewable potential means that within 30 to 40 years, at a given location, this electricity must be competitive with other forms like fossil fuels and electricity from fossil fuels. That will be different, for example, for solar in England than it would be in the Sahara Desert. But we did this separately for every location, and we then looked, this is the demand on electricity in the year 2000, 4,000 terawatt hours of electricity per year. This will be the demand of electricity in the year 2050. In EU and MENA, the doubling comes mainly from the Middle East and North Africa. And now we look at the economic potential of renewables. Wind, biomass, geothermal, and hydropower together can deliver economically around 6,000 terawatt hours per year, so more than enough to supply present demand, 75% of the demand in the year 2050. Now, if we add solar to this, we see that the potential in Europe, Middle East, North Africa to generate economically electricity from renewables is about 150 times higher than the total electricity demand in Europe and MENA today, and still about 100 times higher than the future electricity demand. Solar is by far the most abundant, and if we look at the size of an area which would be required for a gigantic solar thermal power plant which would supply the whole electricity of the world, this would be 1% of the Sahara Desert. Of course, nobody will build a power plant, just one single gigantic power plant. That's not the idea. It's really just to show we are not talking about plastering the world with solar power plants, mirrors, photovoltaics, or whatever. This is the area for the EU 25. That's about 150 times 150 kilometers square. And that would be the solar power plant for 100% German electricity supply. Another example, if we would build a solar thermal power plant with the area of Lake Nasser, this would generate enough electricity, the same amount of energy as the whole oil production of the Middle East together. Now, how is this electricity be generated? We believe for these power plants in North Africa and the Middle East and maybe Southern Europe, it will not be photovoltaics, which will be as a decentralized electricity generation, but for these large power plants, it will be solar thermal power plants. And let me explain to you how they work and why I think that they should be given preference for these applications, not for many others. Here we have a conventional gas turbine, a steam turbine cycle, a pump. Here the steam generator where heat is added in a conventional plant by burning coal, oil, gas, or having a nuclear fission. Then the steam passes through a turbine, the turbine rotates, drives a generator, and the steam is condensed. Now, a solar thermal power plant is using the same thermodynamic cycle, with the only difference being that the heat is provided by concentrating the solar radiation onto a surface which is then transferring heat for generation of steam. And here we have the three main technologies. These are sort of flat mirrors, a so-called Fresnel type of system, where the flat mirrors are following the sun during the day. We have these parabolic trough systems, which follow the sun from morning to night and focus the sunshine about 80 to 100 times on this horizontal absorber tube. And we have so-called power tower or solar tower systems, where we have almost flat mirrors following the sun and focusing it up to 1,000 times on the top of a tower, where you reach temperatures up to 1,000 degrees. What's the advantage? First of all, these systems can be readily integrated into conventional thermal power plants, which we know. I mean, we have companies who really have a lot of expertise building conventional gas turbine and steam turbine power plants. It can be used to provide firm capacity, because you can combine it with a heat storage and supply electricity even when the sun is not shining, or you can use a fossil backup. You can fire gas or coal or oil when the sun is not shining. It can serve different markets like bulk power, remote power, but also it can be used for desalination. It has already now the lowest cost of solar electricity, and the energy payback time, that means the time to generate so much electricity as the energy that's needed to build the plant in the first place, is only 6 to 12 months. And it's a proven technology with an industrial base. These power plants are not new. About 25 years ago, 9 solar thermal power plants with a total capacity of 350 megawatts have been built in the Californian Mojave Desert and have been operating since. They are still working. We checked some of their mirrors and absorber tubes just 3 years ago. There's no sign of wear or decrease in the reflectivity of the mirrors or the absorptivity of the tubes. These power plants have generated $1.4 billion US in revenues, have fed 11 billion kilowatt hour into the Californian grid, and have now levelized electricity costs of around 12 to 15 cents per kilowatt hour. Since then, there have been new power plants which have been built and taken into operation. What you see here is a 64 megawatt power plant near Las Vegas, taken into operation in 2007. Here we have 2 tower plants in Spain near Seville, one with 10 megawatt, one with 20 megawatt, taken into operation 2007, 2009. And this is the so far, in terms of size, largest solar thermal power plant in the world. It has gone into operation in January this year, and 2 identical ones are already under construction. One is just taken to operation. It's the 50 megawatt solar thermal power plant, and it's a solar parabolic trough plant near Granada in Spain. And the interesting thing here are these 2 big tanks, and they are heat storage, which allow this plant to operate for 7 hours after sunset, or whenever the sun is not shining, to bridge this gap. And with this, they have about 4,000 full load hours per year. I have a small video. This is in German. I apologize for this, but I just wanted to show you some impressions from this power plant. It's about 2 square kilometers of area, 550,000 square meters of parabolic mirrors, and about 100 kilometers of absorber tubes. And as you can see here, we are really talking large-scale engineering. This is a lot of civil and mechanical engineering, and it's connected to a conventional power plant. Here we saw the two large tanks again, which act as heat storage. This is another plant that has just gone into operation in Spain. It's a Fresnel plant with the flat mirrors, and this one uses an air-cooled condenser, so it doesn't need cooling water at all, and it's a very promising technology in terms of cost reduction, but it's still at a much smaller scale. It's 1.5 megawatt only. And there's a lot of going on in Spain. All these locations here are locations where solar thermal power plants are either the red ones already under construction or operation, or are in very advanced stages of development where the land has been purchased, the feed-in tariff has been approved, even the payments of the projects and everything have been approved. And we have a total of 2 gigawatt capacity in Spain in all these different plants, which will be realized over the next few years. And if we look at this worldwide, then we see it's in a much larger scale. There are about 5 gigawatts of capacity under advanced development in the US. There is some activity in Australia, South Africa, North Africa, China, India, and a lot, of course, in Spain, some in Italy, and Greece as well. So in total, we have about 9,000 megawatt or 9 gigawatt of solar thermal power plants in the pipeline. Now the question is, of course, always what's the cost about this? And we don't have to make us any illusion. Such a technology will ultimately only have a breakthrough and become commercial if it becomes cost competitive with existing technologies, meaning with fossil fuels or even nuclear. And here we have the cost development curve. I have here in light blue, if you can see it, this is sort of the typical cost for mid-load electricity using a gas turbine or coal power plant. And I assume, just for the sake of this, that this is only increasing from 6 cents per kilowatt hour in 1980 to 7 or 8 cents in 2050. I think that's very conservative. Reality will probably indicate that this increase will be much steeper, but I'm not going to do any calculations which give us a result where people could say, well, he just assumes fossil is getting exceedingly expensive. So the first solar thermal power plants in California, they were much more expensive than conventional electricity, but costs went down significantly, and then nothing happened for 20 years. Why? Because fossil fuel got so cheap that nobody was building any alternative technologies. I remember oil being less than $10 per barrel, and coal and gas similar. And then only in the early 2000s, 2002, 2003, this started again in Spain, because Spain established a feed-in tariff, the Royal Decree, which subsidized electricity from solar thermal power plants with about 27 cents per kilowatt hour. Suddenly, all over the world, building activities started again, industry got interested, and the predictions from learning curves and the predictions of the relevant industry, the companies who are involved in building, planning, constructing these plants, are that roughly 10 to 15 years from now, this technology will be cost competitive with electricity, mid-load electricity from fossil fuels, and this includes oil, coal if the CO2 is removed and stored underground. Now, what we have here is the capacity of installed plants, which is at the moment still very low. It's increasing. I've shown you the 10 gigawatt in the pipeline. But obviously, once this technology is less expensive than electricity from conventional plants, more and more of these solar thermal plants will be built, because the costs are predictive, and because the electricity is not getting more expensive, because sunshine for the next 5 billion years will be available at no cost to everybody. And so this will mean that a lot of the new power plants which will have to be built will become solar thermal power plants in those areas where this is possible. Why am I so confident that we will be able to get the cost down? This is a question I always get asked. I mean, the first reason is with increasing construction and building activities, we get a mass effect. That's just mass production. More and more identical power plants will be built. Not like now where every power plant is totally a first. The second is that these power plants will become bigger. At the moment, the maximum size is around 50 megawatt, but in the US already, the Spanish company Abengoa has received an order for a 280 megawatt solar thermal power plant, meaning you only need one power block and you just have more mirrors around it. But there's also a lot of technology development in the pipeline which has been developed over the past 20 years. And the first is the so-called direct steam generation, where my institute and Spanish research center CIEMAT have been working on for the past 20 years. Now this is a typical parabolic trough plant. We have oil as a heat transfer medium. The oil is pumped through these through the horizontal pipes, the absorber tubes, which are based in the focus of these parabolic mirrors, and it's heated from, say, 300 degrees to 400 degrees, and then this hot oil is used in steam generators to heat water to boiling temperature, evaporate it, superheat it, and then pass it through a two-stage steam turbine, the condenser again, and so on. Now the next step will be to replace the heat transfer oil by water and evaporate the water directly in the absorber tubes. And as you can see here, we save a lot of hardware, we save the steam generators, and we can go to higher temperatures because the oil is limited to about 400 degrees, even so it's a synthetic oil which costs a fortune. Now this sounds simple, it's not. And Jeff Hewitt will agree with me, having two-phase flow through about 100 parallel channels, each channel being 800 meters long, and to control this and come out here with superheated steam, even if a cloud comes across it, it's not trivial. We have pilot facilities in Spain. We have had about 15 PhD theses. We can do this now. We can control it. We can predict it. And we are now in the process of setting up a pilot facility with 3 to 5 of these parallel streams, each of them being 2 megawatt thermal, to demonstrate that this works, and then it's ready for installation. And this will reduce the investment cost or the electricity generating cost by roughly 15%, just because of the higher temperature and the less hardware. That's one thing. The next thing is solar gas turbine, steam turbine cycles. Probably all of you or most of you would know that the highest conventional power plant cycle is a combined cycle plant where we have a gas turbine and the air is compressed, heated to 1,000 degrees by burning gas, then expands in the turbine, drives the generator, and the hot exhaust gas is used to raise steam, which is then expanded in a steam turbine to raise electricity. Now the same cycle can be realized with a solar power plant where we have a solar tower and the heliostats, and we use solar energy instead of gas or together with gas if the sun is not shining to drive the gas turbine. And that gives us efficiencies of up to 35%, meaning we need less mirrors, which make 40% of the investment cost for the same amount of electricity. And again, this has been developed and demonstrated in the last 10 years. What you see here is one single absorber which would be sitting on top of a tower. This is only for about 500 kilowatts. There will be many of those, and the air comes in here under pressure, moves here through a ceramic sponge, is heated to up to 1,000 degrees, and leaves then here with 5 to 10 bar pressure and 1,000 degrees to go into the gas turbine. And there are a few tricky bits like this glass here, which can only take up to 600 degrees, even so we reach 1,000 back here. But we have demonstrated this in the tower in Almeria in Spain with 3 of those receivers. They sit here, and the actual gas turbine is this small thing down here running at 250 kilowatts. and we are presently together with some companies like Abengoa, like MAN, building, and Endesa building a demonstrator at 4.5 megawatt near Spain, near Sevilla in Spain. The third reason why I believe in the potential of solar thermal is the ability to store energy. Photovoltaics and wind may become cheaper than this technology, but they only produce electricity when the sun is shining or the wind is blowing, which means it's relatively low-grade electricity which will be there or it will not be there, just depending on the weather conditions, and certainly not after sunset in terms of photovoltaic. Solar thermal has the advantage you store heat. That means the excess heat that you don't need in the afternoon, you store, and then you withdraw it from a heat storage like this oil tank or this liquid salt tank to generate steam after sunset. Now, this is the existing technology. It works in Spain, but it's not trivial and it's not terribly elegant. It's two large tanks, 36 meters diameter, 15 meters tall. In this tank is about 25,000 tons of a liquid salt. It's a sodium nitrate, potassium nitrate mixture which melts around 180 degrees, but which stays liquid. And you heat it during the day to 400 degrees, and at night you cool it down again to 250 degrees, and you use the resulting energy to raise steam to run the power block. The cost of this is, for a 50 megawatt plant, around 30 million euro for the salt and for the tank. We have since developed a new technology together with a large civil engineering company, and that's a concrete heat storage. We developed together with them a special concrete which has a lot of beneficial properties, which I don't want to mention in detail now, you can ask later. And this concrete heat storage is heated during the day with excess heat to 450 or 500 degrees, and then it's cooled down again, and the sensible heat is used to raise the steam. So it's the same as the liquid salt. The only difference is this is 40% less investment cost than the molten salt. And that means about 20 million instead of 30 million investment. And we have been running this since May last year continuously through cycles, and there's no degradation, no deterioration in this, and we just keep it running. And this is how it's going to look on a large scale. We will have about 20 of those concrete blocks together to form one package, which is then insulated on the outside against heat losses. And we will have a number of these blocks together, then connected through pipes like this. And here, during the daytime, the hot oil comes in, heats up the concrete blocks, and leaves at a lower temperature. And at night, it will just be the other way around. The cold oil comes in, is heated up, comes out hot. This sounds like a fairly big thing. It is. But if you look at it, this is a solar thermal power plant in California. And this is the area required for the concrete heat storage. We need about 50,000 meter cube of concrete for a 6-hour storage for a 50 megawatt power plant. That's 6 hours full load electricity. Now, this is already a big step forward, but it's still not as elegant and effective as we want to have it, because if you produce steam, steam evaporates at a constant temperature. If you do this evaporation with sensible heat transfer, your exergy losses are dramatic, because you have to come in start with a much higher temperature than the boiling temperature, and then the concrete blocks go down in temperature, and so you lose the exergy at the beginning. So we have developed a latent heat storage where we melt and solidify the salt and use the heat of solidification. And that's what we have here, lab scale, pilot scale. And at the moment we are setting up, together with an industrial consortium in the south of Spain, a unit which consists of a concrete heat store for preheating the water to boiling temperature, a latent heat store for evaporating it, and another concrete heat storage for superheating it. Now, where are these power plants going to be built? And this is one of the nice things. This is an advantage if you work for the German Aerospace Center, because we have access to satellite data without end. We have satellite data for the surface of the Earth for the past 25 years, 3 square kilometer resolution, 30-minute time intervals, cloud coverage, aerosols, water vapor in the atmosphere. And from these data, we can calculate the direct radiation for any spot on the Earth at any time of the year, averaged over 25 years. So we really don't depend on a good year or a bad year. We can say this is what it's going to be in average on June the 13th at 2 o'clock in the afternoon, for example. Now with this data and our models for the whole system, we can calculate the generated electricity at a given location, again, over the year and time. And if we then combine this with geographic information data on the slope, so we filter out everything where it's not enough flat land to build a solar power plant. We filter out all the type of land which is not suitable, cities, agriculture, military security zones, sand, water, everything that's not suitable. Then we end up with the area where actually those solar thermal power plants can be built. And we combine this with infrastructure costs, available roads, available power lines, insurance costs like danger of tsunami, to get the total cost of electricity generation. And this then allows us locally to do a ranking of sites. This is, for example, Spain. Only the white areas here are suitable for solar thermal power plants. All the other areas are excluded for whatever reasons. And if we then combine, now this is just changed in color, everything which is white here is not white here, then we can see the most suitable sites in terms of ranking, like down here. That's the sites where in Spain we can build with today's technology the most effective solar thermal power plant, and the more it moves to red or darker, the more expensive the electricity will be. And we can do this for the whole world. This is the north of Africa. The cheapest areas are here, Egypt or Morocco here, and it gets more expensive as we move inland because the condensers have to be cooled by air rather than by cooling water. Now, everything that's green here are areas theoretically suitable for solar thermal power plants. This looks wonderful, doesn't it? Unfortunately, life is never that easy. This is a picture of the world at night from satellites, and all the green areas are areas where you have a lot of light at night. And if I just equate the demand for light with the demand for electricity, you see the areas where we have a lot of demand for electricity. We don't have a lot of sunshine for solar power plants, and the areas where we have a lot of potential for solar thermal power plants, we don't really need that much electricity. So we don't really have an energy problem, we have an energy distribution problem. And how do we solve this? 30 years ago, my predecessors suggested to build electrolysis plants in North Africa, use solar thermal electricity, generate hydrogen, transport it to Europe, and use fuel cells. Now you lose 75% of the energy doing this, and the costs of the fuel cells are even today excessive. Second option, alternating current lines with the normal current 380 kilovolts or 800 kilovolts. You only lose 45 to 25%, but that's still excessive. The solution will be high voltage, direct current lines, where you only lose 10% of the electricity over 3,000 kilometers from the north of Africa all the way to Europe. And this is again proven technology. There are about 100 high voltage direct current lines already in operation worldwide, and Siemens and ABB are presently building a 2,000 kilometer line for 6.4 gigawatt capacity within China, with losses over this distance of only 7%, including the losses occurring when you go from AC to DC and back to AC. Now, how is this whole thing developing? And now we are at the so-called Desertec scenario. How could this whole thing develop with building power plants in North Africa and in the Middle East and transporting it to Europe? Here in dark blue, we have the increasing electricity, moderately increasing electricity demand in Europe. Here in dark red, the strongly increasing electricity demand in the Middle East and North Africa. And in dark gray, the capacity of the power plants in MENA existing today. And clearly, the difference between the red bars and the dark gray bars are new power plant capacities which have to be installed and built. This will initially be done in the next years to come by building new conventional power plants. Gas, oil, maybe coal, maybe nuclear. But there will also be the first solar thermal power plants. Power plants are at the moment already under construction. And once these power plants will produce electricity cheaper than the conventional power plants, one will increasingly build in North Africa and the Middle East the solar thermal power plants, just because one saves money and one saves fossil fuels which can be exported. So that's the capacity increase, and most of this capacity will be used for their own electricity consumption plus additional desalination plants, because water is going to be the main problem in these countries. Already today in Yemen, in Sana'a, the water table drops 6 meters per year. Egypt will need the water of a second Nile in 30 years. And there will be no natural second Nile. It has to be desalination, which in the Mediterranean is done using reverse osmosis driven by electricity. And from 2025 onward, one can envisage the first electricity exports over the Mediterranean into Europe, reaching roughly a capacity of 100 gigawatts, in 2050, which makes about 15% of the European electricity consumption. And this is how this looks in terms of numbers. In 2050, one could envisage having 20 high voltage direct current lines from different positions crossing the Mediterranean, like going through Spain or through Sardinia and Italy, or around Egypt and Istanbul into Eastern Europe, providing electricity of around 7,000 hours per year with heat storage at a cost of 6 to 8 cents per kilowatt hour in today's electricity costs. I mean, this will be inflated, of course, like everything else, which is similar to a coal power plant with CO2 sequestration. The area required for this is 50 kilometers times 50 kilometers, or 0.025% of the Sahara area, plus the area required for the power lines in Europe. And the cost for this would be roughly 400 billion euro, which is the cost of the Desertec project, which is publicized at the moment ever so often. And how would this look in a total mix? That is a scenario for Europe and the Middle East and North Africa, which would achieve our CO2 reduction targets by the year 2050, and which would make a large use of renewables. What we have here is the diamonds here is the peak power that's required at the moment, or which is predicted for 2050. So the maximum electricity demand at any time in the year. We say we always want to have 20%, 25% reserve capacity, which is common practice today. So these are the triangles. This is what we have to be able to provide at any time. And this will be provided by a mix of energy technologies. First of all, we have the fossil, oil, gas, coal, nuclear. Then we have the fluctuating renewables, photovoltaics, wind. And then we have the storable or dispatchable renewables such as solar, thermal, and biomass and geothermal. And what we say is when we have the local fluctuating electricity available, it will be fed into the grid preferentially. The whole scenario will then look like this. Today, fossil power plants or conventional power plants are operating an average of 5,000 hours per year, including the peaking plants which provide peak electricity or mid-load electricity. In 2050, this would go down to 2,000 hours per year. That means fossil power plants will almost exclusively be used to provide peak power when the fluctuating renewables and the storable or dispatchable renewables are not able to provide enough electricity. And from this solar thermal electricity, that's the amount that will be exported from Africa to Europe, and this is the amount that will be used within Africa and the Middle East. And this system will reduce CO2 emissions to 80 to 38% of the year 2000 values, and it will also reduce the EU fuel imports for electricity generation from 80%, as the business as usual case for 2050 would be, to 32%. So let me come to some conclusions. In 15 to 20 years, it may be possible to realize an electricity supply which is both less expensive and significantly more environmentally friendly than the present technology mix. The increased use of local renewable energy sources will reduce the dependency on imported energy carriers. Solar thermal power plants in the MENA region will make a significant contribution to this, and there is no competition between photovoltaics, wind, and solar thermal power plants. In the contrary, there's a synergy because the increased contribution of solar thermal, which is dispatchable and plannable, allows us to use the fluctuating renewables to a much higher percentage. On 13th of July this year, the so-called Desertec Industrial Initiative was established, which has the aim of providing 15% of the European electricity from renewables originating from the MENA region by the year 2050. This industrial initiative at the moment consists of 12 major companies. I think 2 or 3 of them are represented here even tonight. It has already 8 additional companies which have signed but are not to be named yet. And it's, of course, the aim is to make this a truly European and MENA activity rather than just one originating from a small number of companies. Now, the MENA countries will benefit from this concept in a number of terms. First of all, they will be able to produce sustainable electricity for their own ever-increasing demands. There will be increased employment and jobs. About 75% of the value generation occurs locally for the building of the power plants, all the concrete, steel, the main components. And there will also be qualified jobs. I think this is the best development aid one can ever provide, jobs and education. There will be income from electricity exports, and the electricity from the solar thermal power plants will be used for desalination to provide fresh water for irrigation and human consumption. From a technical point of view, this Desertec scenario can already be realized today. We have enough technological experience and we have the industries available to build these power plants and to build the power lines. However, of course, if you look at the cost, substantial financial support will be available. One would need roughly, and this is really just a ballpark number, 50 billion euro subsidies at the beginning to move the cost regression curve to a value where it becomes competitive with the other electricity types. And after that, it becomes, it runs by itself because the investment pays back in terms of electricity sales. But this investment in terms of CO2 trading, in terms of subsidies, in terms of feed-in tariffs and many other mechanisms will have to be provided, and we cannot expect the countries in North Africa to do this. Here, Europe and the European politics, countries on industry have to assist. The countries can provide land and other, and say a secured supply and guaranteed supply of electricity later on. But the main thing, and this I think is the very critical issue, it's the political support. Technology we can do, the money I think we can do. After all, 50 billion, a year ago, 50 billion would be a real shocker. And now 50 billion is just half the money of saving a major bank. It's half the money the US spends every year on the Iraq war. So this money can be invested. But the political support to getting all these countries together and draw in the same direction without their own interests, that will be a difficult thing, and I think that's the challenge. The Desertec initiative or the Mediterranean Solar Plan, or whatever they may be called, will face in the future. However, a lot of things have happened so in the past year. There's a lot of political support coming up from different countries, and maybe these objects in the mirror are closer than they appear. Thank you very much.
Okay, I'll now ask for questions from the floor. What I'll do in each case is refer them to Hans in the first instance, and then ask Walt or Nick if there's anything they would also like to add. Gentleman here. Here being there, yeah.
Yes, from FSK. I'd just like, we had a meeting in July on the Mediterranean Solar Plan, which was attended by a few people here. Phil Eames was one of the chairman. Just like to point out, just to fill in, I think Walt made some good points. There was a meeting...
Could you speak into the microphone?
Yes, there was a meeting at which Piebalgs, the EU Commissioner, within the last week or so, was talking about energy security in Europe. And it was on Desertec and Nabucco, the gas pipeline. And he announced that next month there's going to be a conference between the EU and the MENA, Middle East, North African countries, to look at the political aspects. So there can't be a land grab, in North Africa. That just wouldn't be right. And that really is the key aspect. The technical problems are no longer an issue. It's the political issues that the EU has realised are the ones they're going to have to deal with. So next month, I don't have the details, unfortunately. Next month is going to be a political conference to look at those kind of issues with the MENA countries. I'd also like to say that Noor Energy, who are a London-based company, are at the moment looking at an Italian Tunisian link for 2 gigawatts. So that's a very substantial project they're looking at the moment. And as Walt says, you don't want individual ones, but that's actually on the go at the moment. Also like to say that today the Hadley Centre's latest report was published, where they're talking in apocalyptic terms about climate change, not just 2 degrees, but 3 and 4 degrees. So this issue about decarbonisation of energy supplies, we're talking about, I know you had on your slide 2,000 gigawatts peak, Hans, but I think we're going to be talking about 2,000 gigawatt means and much higher amounts. And in fact, our ambition should be much higher than the levels that you are talking about. we should be talking very, very large amounts of solar power indeed. And I know David Mackay has only becomes the DEC Chief Scientific Advisor on Thursday, apparently. He's now talking about large amounts of nuclear in Britain. And I suggest to you that this way is one way of avoiding large amounts of nuclear power.
I suggest that we don't go into the details of the latest figures came out from the Hadley Centre, partly because I don't think anyone here has looked at them in detail, partly because I know that some of the people associated with the Hadley Centre are not totally happy with them. But let's start with the obvious point that we need very much more renewable capacity, and this is part of it. Do you want to respond to the first part of that question, Nancy?
Yes, I mean, what we have tried to make is a scenario which is not just environmentally sound, but also economically sound, because at the end it has to be affordable. And we feel from the percentage of renewables that we have, combination of imported and local ones, that this is for Europe. Actually, it would be 80% renewables by 2050, which is for electricity, which is the target of the European Union at the moment.
No, I'm sure the conclusion that this is, this is potentially an important part of the renewables capacity and could offset some nuclear generating capacity. I'm sure that conclusion has to be right. This gentleman there, and then I'll come to the gentleman in the front row.
I think one of the big constraints, and it's going to become more important, is the business of water. You did mention that, but I was just a bit confused by your numbers. On about slide 6 or 7 or something like that, you showed a kilometre of land could produce, I think it was 200 to 300 gigawatts, and could desalinate, I think I wrote down 165,000 cubic metres of water. But I wasn't sure whether some of those gigawatts were going into the desalination. If so, how much? And how much of that generation was net after the desalination? I'm really interested in how much energy is required for how much water desalination. If I may, just have a quick word that this is the perfect partner for wind energy, our fickle energy. If we go for nuclear, as we know, with current technology, it's unresponsive and would be reliant upon coal, and the sequestration of that is unproven as yet at scale.
Okay, I mean, this thing here, since the desalination in the Mediterranean will be almost exclusively done by reverse osmosis, that means all the electricity generated would be used for desalination. But the number shown here, where I said 1 square kilometer will produce that much water, that is under the assumption that all the solar energy ultimately is transferred into generating fresh water with the, in this case, most efficient technology in the Mediterranean. In the Middle East, or rather in the Gulf region, the salt content is so high that presently mainly thermal desalination plants are installed, and there one could combine the condenser of the solar thermal power plant with a desalination unit, a thermal desalination unit. That would reduce the efficiency of electricity generation, but also produce fresh water. It depends on the location.
One further comment on that came up in earlier meetings that I've attended is that if you are wanting to have a desalination component to a particular installation, obviously you're going to want to locate it as close as possible to the seacoast.
Yep.
And that is not necessarily the ideal location for solar insulation, because of the possible cloud cover and mist and effects of that kind. So there is a trade-off that you should be aware of. Incidentally, with regard to the earlier question and the politics of this issue, I don't think you should be under any illusions that if this Desertec concept does begin to attract serious political commitment, one of the major opposition activities will arise from the nuclear people.
There's a question in the front here.
Well, I was just thinking, what is the problem with VLS photovoltaic, very large-scale photovoltaic? In many papers we are finding now for the desert area, large-scale photovoltaic is also possible. So what is because in thermal you need water. Water will be a big problem in desert area. That is also true. But what is the problem with very large-scale photovoltaic?
No electricity at night.
But if you have a very long transmission line, then at least...
Then you will still have no electricity at night.
You can cover 16, at least 16 hours you can cover with photovoltaic.
If you look at the east-west in Africa, that's correct, but it's still not a dispatchable electricity. Like you cannot put in more into the grid at any time than the sun is just producing, which you can do with a solar thermal plant by just taking something out of the storage. The other thing is, of course, when solar thermal power plants in the desert will be operated with air-cooled condensers. This reduces the efficiency by 3 to 4 percentage points, say with a conventional plant, 16 to 17% to 13%. So you don't need the cooling water if you can cope with the reduced efficiency. So the main issues are costs and plannability and dispatchability.
Could I just amplify that a bit? There must be fairly large exergy losses in the storage system. So if someone came up with an effective electricity storage system, that might change the balance between solar thermal and photovoltaic?
Absolutely, yeah. I mean, if you come up with a very effective electricity storage system, that could certainly change the balance. But there are things like compressed air energy storage or adiabatic compressed air energy storage. But they don't have the density, and they depend on the availability of underground caverns. In the areas where you have a lot of sunshine, typically there is not much water for hydro storage. So it's the storage problem, unless you come up with some thermoelectric type of storage or electrochemical type of storage.
Or you can go for palm storage scheme. In fact, we are thinking about in India. I'm from India. I am attending the conference. So we are thinking to go for a solar thermal photovoltaic in a big way with a palm storage scheme, which is 1,000 megawatt, palm storage scheme, which will pump through photovoltaic during daytime, and during nighttime peak hours will be using that power.
But you need a place to pump it up.
Yeah, there are many sites. There are worldwide.
Not in North Africa.
Not in North Africa.
Okay, but that is
if mountains are close, then you have typically the problem that you don't have enough flat area. So
okay.
If you solve the storage problem, it's a different story.
Yeah, that is my point.
Can I inject a slight dissident view here? I am hoping that we are eventually going to drag ourselves away from the traditional mindset, which assumes that any electricity system has to be made up of a bunch of absolutely independent loads to which the generation has to respond all the time, no matter what the status of the load or how it is actually being operated. I am hoping we are going eventually to bring ourselves into the 21st century and start realizing that most electrical loads themselves are variable or actually intermittent, and that many of them are not particularly time sensitive, and that there is the possibility now, with the information and control technology we have available, to have the loads participate in the balancing operation of an electricity network, in which case the whole dispatchability argument moves out of the foreground. It's still interesting, but it is no longer a deal breaker. Yeah. If you have the possibility of having, say, your deep freezes, your fridges, your washing machines, a lot of industrial heating, various things of that kind, actually on and off according to what the status of the rest of the system is, then you will find, for example, that if you've got a lot of wind power coming in at 3 a.m., you can set your washing machine or your dishwasher to turn on at 3 a.m. when the wind power is available. I mean, that kind of operating regime for electricity is something we ought to be working toward.
I fully agree. I mean, load management is an important contribution as well, same as efficient use of electricity or any form of energy. I don't think it's that easy. I mean, you can't switch off a chemical plant and on just depending on how the electricity is supplied. As there are things that just need electricity and that generate a peak.
But a paper mill or a chip plant, but
and the problem is with all the air conditioning units, you also don't want to switch them off during peak demand.
Gentleman in the second row here.
You said that the direct steam generation simplifies the flow sheet. You also said that if you are able to take care of the two-phase flow, you can really get the same kind of a better efficiency. My question is that how are you going to take care of the storage of 540 degrees superheated steam when you're generating to a direct steam generation in your vacuum evacuated tubes? And what kind of a storage system you have to do, because you will have to necessarily go away from the molten salt. That's the first part of the question. And second one is that it's just a theoretical question that I'm asking. Is it possible that the kind of furnace that you are designing, DLR, in terms of converting that into a splitting of water through a iodine sulfur reaction and generating hydrogen, and instead of going through a HVDC lines and doing the intercontinental transfer, hydrogen, if you are able to transfer it with a much higher concentrated energy per meter cube of the energy, which can be used even for the transport sector, and not only for the power generation sector, you can use it for many other applications. Has it at least been a theoretical study done to this? And last question is on that concrete storage. I mean, with the specific heat of the concrete being only 0.21, the heat losses from the concrete is going to be far larger, and how does that really compensate for the overall heat rate of the cycle? So, pardon me for asking 3 questions in one packet.
Okay, I hope I remember them all. I mean, for direct steam generation, you would use a combination of a concrete heat storage for heating to boiling temperature, a phase change heat storage for evaporation, and a concrete heat storage for superheating. This is what we're demonstrating at the moment. The next thing was the hydrogen generation. Yes, we have the Hydrosol project where we directly split water molecules with the thermochemical cycle with about half the energy requirement as going through electricity and electrolysis. But it's still less efficient than transferring the electricity directly, because at the end you have to use the hydrogen somewhere to make electricity out of it. I think this will be interesting when we move to a much more wide-scale use of hydrogen in fuel cells, for example. But this is much longer term. And the last thing, if I remember correctly, were the heat losses. The heat losses of the concrete heat storage are very low. They are almost negligible. I mean, you have such a large volume to area ratio that the same for the molten salt. This is only a very small percentage. I mean, don't forget, we are not storing over days. We are just storing over hours. I mean, one uses after sunset the stored heat to generate into electricity. It's not keeping it for a few days for a bad day. It's really just storage of hours, and so the losses are very, very small.
Hence, I can believe it that the heat losses are small, but aren't the exergy losses significant?
The exergy losses are, of course, significant with any storage medium. And this is why the combination of concrete, phase change concrete, we are following the evaporation curve much closer. You know, if you look at the temperature entropy diagram or any type of diagram you use for a Rankine cycle, enthalpy entropy diagram, we're really following the line where we have heating, evaporation, superheating.
There's a question here, and then a gentleman at the back. Yes. Yes.
Still on the subject of energy storage, which seems to be one of the key problems, I'm surprised that concrete comes into it, because concrete is a material which has been optimized over 150 years or so against criteria which do not include energy storage, as far as I know. And also, it's a very heavy material to transport, and you don't necessarily find the right materials for it in desert areas. So the question is any research being done to improve on concrete as the preferred energy storage material?
Okay. I mean, first of all, this is not the same concrete that you use for building. I mean, this is a specially designed concrete where the additives, the mix, as well as the additives to the water have specifically been designed to produce this concrete which is particularly suitable for heat storage at high temperatures. We have also looked at a wide range of other materials, and in terms of cost benefit, the concrete so far was really good. And it's also a material that's very widely available. I mean, sand is no problem in the desert. And of course, you have to transport the other components there. But it's worldwide, very widely used. It's not that you transport the blocks. You make these storage units on the site. So we are still looking, but we went through a whole screening process of different materials. What we are now looking at is using reversible chemical high-temperature reactions. That would, of course, be very elegant. It would be at the same temperature, or you can introduce a temperature glide, whatever you want. But this is still at a very early stage because you need not just the stored capacity, you need also the energy rate because you want to get 50 megawatt, not just a certain amount of kilojoules out of it. And so to get both the thermal conductivity and the transport properties as well as the storage capacity, this is the tricky thing.
Yeah. There's a gentleman in the far corner, had his hand up next, and then three here.
Your graph at the beginning seemed to say that you expect cost parity with fossil fuels around 2025, and that was mainly due to economies of scale? Or maybe
no, we expect, and that's from industry, grid parity between 2020. No, not grid parity, sorry. We don't expect, this is the difference. I mean, photovoltaics always talks about grid parity. We are talking about achieving electricity generation costs. Right. Which is a totally different thing to getting the electricity that you buy at home in 2020, roughly 25. And this is due to economies of scale, due to larger units, mass production, but also due to phasing in of new developments which have already been in the pipeline and under development and demonstration for a long time. So it's a mix of this. Any learning curve is not just mass production, it also includes innovation.
Thank you. That covers my question.
There was a question over here.
Stephen Cheese. 3 points. You mentioned short-term storage. Surely one... Sorry, start again. Stephen Teeds. You mentioned short-term storage. Surely a very major part of the problem is long-term storage or longer-term storage because the demand fluctuates so dramatically over time and also in Europe depending on seasons. The second one, somebody mentioned that you didn't want individual projects. Surely you would be delighted to have individual projects politically because it will actually get industry far more involved, perhaps raise rather more of the money than government may want to. So one would have thought that one would like to bring as many organizations and large bodies in as one possibly can. And the third one that worries me slightly is the political one mentioned by Professor Patterson. We know what can happen in Russia, etc. Surely one would need to have this dispersed not just in Africa, but very large projects somewhere else as well as a balancing potential.
Okay. I hope I remember it all. Let's start with the last one.
Yes.
We said it's 15% of European electricity demand, and at any time we have 25% excess capacity. So even if some idiot would cut off all 20 power lines, there would still be enough capacity in Europe from the existing local power plants and local renewables with this scenario. So there was no complete dependency. Now the next thing is you said there is a distribution over the season. Absolutely right. But you go to North Africa, there's blue sky and sunshine 360 days in a year. And so even now in Spain, they can predict the electricity they feed into the grid 30 hours ahead. They have to, otherwise they lose their tariff. So it's really plannable. And with the exception of these 5 days in North Africa, you can produce the electricity throughout the year.
There were two other questions. Can you summarise them?
Yes, well, I think I'm more worried that if you can't store it for longer, you can't actually use it. In that case, it definitely becomes a waste resource. So my question really was, without being able to store for rather longer, one can go on producing the stuff all the time in the Sahara, but you can't actually store it all the time.
Okay.
That's really the point. The third one was this one of needing a balancing of projects around the world if one is going to avoid being taken for ransom.
Okay, I mean, the thing you would do certainly is, you would use the electricity from renewables preferentially, like, for example, in the German feed-in tariff. That means if the heat storage is full, and there is electricity to come, one would then use less fossil power plants. This is why the actual operating time goes down, and why the fossil power plants would have to be peaking plants or mid-load plants which can be regulated.
Just picking up that point, of course, we're talking here about a system which is integrated over not just a continent, but two continents, and clearly the level of integration is going to have to be a little bit carefully managed. But I think that as well as having this very long range part of the system, the other end of the system is also going to evolve, so that we're going to have a lot more small-scale generation much closer to loads, including right on the premises in many instances with micro-cogeneration and photovoltaic roofs and what have you. And so you have a vastly increased portfolio of variety on the whole system. It isn't a question of either you get CSP or the lights go out. The CSP will be contributing to a very, very complex mix and a very complex system-wide operation, at least conceivably extending right across, thousands of kilometers. So this is, in fact, that's one of the things that I think we have to take into account, that the system cannot be too tightly integrated. You don't want to be able to collapse the entire network if something goes down. So you really are going to have to loosen up some of the operation.
I'll take two more questions from people who had already got their hands up then. Yeah, front row.
Dan Davis, interested in your storage system again, and one of the things that strikes me, if it's that efficient, the numbers sound very good, why can't we put these on existing thermal power stations instead of building pump storage systems?
Actually, we are at the moment just in the process of doing some pilot projects with this, not just with power stations. It has a number of applications, like if you have combined heat power systems, which are at the moment operated on a heat demand cycle. You can decouple heat and electricity. We are working with the chemical industry in a number of processes where your heat supply and demand is not synchronized with foundries and other applications.
Much cheaper than pump storage.
Yeah. Absolutely.
There was a question in the third or fourth row over here.
I got the answer.
You got the answer? Okay. Well, in that case, I'm going to ask my other colleagues on the platform here to wrap it up, starting with Nick. You've got some more points.
Okay. Well, the only point I think I would ask is that although we've obviously had a most interesting discussion on the development of the large project, I wasn't completely clear on the technology development route of these very large installations. We ended up talking about injections of 6.4 gigawatts times 20, I think. But how do we get there, and recognizing that generally developments of that scale will have a number of hiccups?
Well, okay, I mean, you're building a power line. One would hope that there are no hiccups. I mean, Siemens is just building a 6.4 gigawatt line.
No, I was referring to what's on the end of the line.
On the end of the line?
Oh, yes. Well, because at the moment, if I've got it right, there are a number of really rather small installations being built, but I didn't see any route through to this massive installation that we ended up talking about.
Well, at the moment, there is sort of an optimum size of somewhere in the 500 megawatt range. Because if you make it too big, the heat losses in the piping will be too high before the steam or whatever it is reaches the turbine. So it will have to be a connection of these power plants. So it will be large units, but we will not have like a 5 gigawatt plant or something like that.
When do you hope to build and test your 500 megawatt building block?
Well, they are now, as I said, the first 280 megawatt plant the order has been placed in the US. This is a plant that they will have, I think, 3 steam turbines and a parabolic trough. So this is Abengoa is the project developer and designer, and they will build this in California. So that's the next scale.
I come back to the original comment that I made. My gut feeling is that I would like to see this happen, although I know it isn't going to happen in my lifetime, but I would like to see a roadmap. I'd like to see some kind of clearly laid out political, institutional, and financial pathway. The technical part I think we can take care of. There are a lot of life cycle questions and things of that kind that still have to be answered. But the technical part doesn't bother me. The part that does bother me is whether we can actually get the political will, and with the political will, the necessary institutional and financial structure to make something as ambitious and potentially as landmark as something of this kind. And all I can say is I wish you well.
Can I just add to that, Hans, and then I'm going to give you the last word.
Okay.
High voltage DC connectors do exist. Oh, yeah. And for example, the Nordic system has shown the advantages of linking different energy systems, but that's between Norway, Sweden, Denmark and Finland, 4 countries with very similar culture and a natural tendency to want to agree and find consensus. When I hear 20 high voltage DC connectors across the Mediterranean, I tend to agree with Walt. It seems to me that that's a political nightmare.
Nobody has said it's going to be easy, but at the end, I mean, coming from the German Aerospace Center, I have to say we managed to get the man to the moon, and you have to set your targets high. The other thing, just to answer,
you have to do it with Colonel Gaddafi.
Yeah. Well, true, but we are looking at a 40-year time span. Now, just to answer your other questions, I mean, rumor says that I'm going to be on the advisory board of the Desertec Industrial Initiative, which for the next 3 years exactly has set itself the target to come up with this roadmap. So maybe 3 years from now I can report here how this is going to happen.
Excellent. I hope I'm still around to hear you.
Thank you very much, Hans.